Welcome to lecture 16th of second unit Polymer Science and Technology. In this lecture we will see the step polymerization and reaction kinetics of step polymerization. We have already discussed the step polymerization in unit 1. Here in this unit, second unit, which is dedicated to the polymerization reaction kinetics, we will see the kinetics aspect of the polymerization reaction. So we are taking the example of polyester. Polyester is made up of a diacid and a diol. Diacid is a monomer which contains two carboxylic group at the each end, and diol is another monomer which is having two hydroxyl OH group at the either end of the monomer. Okay. When diacid and diol will react, they will form a polyester. The polyester is basically COO group. So if COO group is present in a polymer, then that's mean that polymer is a polyester. So for example, we are taking a diacid. This zigzag line shows some rest of the part which is not shown. We are just considering the functional group of the monomer. So here we can see that this is the monomer. At the end of this monomer there is one carboxylic group, COOH. Similarly, there is another carboxylic group which is attached to the left hand side of this monomer. That's why this acid is known as the diacid. That's mean it contains two acidic group or two carboxylic group. So diacid will react with a catalyst. This catalyst is HA. This catalyst is capable of donating one hydrogen when required. So first of all, diacid will react with the catalyst, and this will be a reversible reaction. K1 the forward rate constant, K2 is the reverse rate constant, and an intermediate species 1 will be formed, and this species 1 is COH, OH and A negative. Okay, this A negative comes from the catalyst. So this is the intermediate which will be formed momentarily for the fraction of second, very you can say for the microsecond kind of duration. Then immediately this species 1 will react with the second monomer diol. Here you can see we have only shown the one functional group, OH group, on the right hand side, and there must be something which is shown as the zigzag line, and this may be different in case of different monomers. So just to generalize it, we have just shown as a zigzag line, and keep it in mind that there is another OH group which is present on the left hand side of the diol. That's why this is known diol. So species 1 will react with the diol. This is another reversible kind of reaction with the K3 forward rate constant, K4 is the reverse rate constant, and when species 1 will react with the diol, you can see this diol will get attached to the carbon at its valency where positive charge was there, and this zigzag line shows that the polymeric chain is attached to here and another polymeric chain attached to the hydroxyl group. So this is the second species that will also be formed for a moment. This duration may be something in order of micro or milliseconds. Again, this species 2 will undergo condensation reaction, and condensation reaction is again a reversible kind of reaction with the forward rate constant K5. We have not shown the reverse rate constant K6 because this is my final step, and we are interested only in the product or the polymer, which is a polyester. So this species 2 will undergo condensation reaction, and by condensing out one water molecule, it will be converted into polyester. You can see there is 1 2 3 3H 3 hydroxyl group, 1, 2 and 3, and 3 oxygen. So one OH group is on the left hand side, which is not shown, and you can see that polyester and water as a product of this reaction. So polyester is a polymer which is having ester group. COO group is the ester group, and this water molecule which is coming out of the reaction as a byproduct is the condensation product, or you can say it is a product that will form during the polycondensation reaction. That's why this type of step polymerization reactions are known as polycondensation reaction, because here water is condensing out. Okay, so if the mechanism of the step polymerization is clear, then we will move for the kinetics. Now rate of the polymerization can be followed by the rate of disappearance of monomer, or we can say the rate of the polymerization can also be followed by the rate of appearance of the final product. But for simplicity, it is customary to take the rate of disappearance of the reactant. In our case, the rate of disappearance of the reactant is the rate of disappearance of the monomer. So we will select either of the monomer, either a diacid or diol concentration. So in this example, we are considering we are following the concentration of the diacid. So Rp, which is the rate of polymerization, is equal to negative, means why negative? Because as the polymerization reaction will proceed, the concentration of the diacid or another monomer diol will decrease with respect to time. Okay, so it will be minus d by dt concentration of carboxylic group present in the polymerization system at any given time t. Now rate of the polymerization is equal to, you can say, K3, which is the forward rate constant when my diol is reacting with the species 1 in the step 2 and forming the species 2. So rate constant K3 multiplied by the concentration of the species 2 multiplied by the concentration of the hydroxyl group. Why hydroxyl group? Because this is the diol which is reacting with the species 1. So concentration of species 1 multiplied by the concentration of the hydroxyl group. Okay, but here the concentration of the second intermediate is very difficult to measure the concentration of the intermediates, because they will appear momentarily during the polymerization reaction and then they will disappear. So it is very difficult to measure. So we have to replace the concentration of the species 2 with some other term. We know that at the equilibrium, because in case of any reversible reaction, after some time equilibrium is attained, and when equilibrium is attained, then the forward rate of the reaction is equal to reversible rate of the reaction. Okay, so we can say the equilibrium constant capital K is equal to K1 over K2, where K1 and K2 are taken as the forward and backward rate constants. So this will be equal to the concentration of my second intermediate divided by the concentration of the carboxylic group and concentration of catalyst HA, which is in step 1, concentration of carboxylic group and concentration of the catalyst. This will be, and rate constants are K1 and K2, and the product is species 1. Getting my point? Okay, so we can write as concentration of my species 1 is equal to equilibrium rate constant multiplied by the concentration of carboxylic group multiplied by the concentration of the externally added catalyst HA. So now we have converted this concentration of my intermediate 1. This is actually intermediate 1. Intermediate 2 is this one. We are not considering intermediate 2 here. This is intermediate 1. I think I wrongly said earlier it's as a intermediate 2. This is a intermediate 1. So okay, you can correct it. So the concentration of intermediate 1 is equal to equilibrium rate constant multiplied by the concentration of the carboxylic group multiplied by the concentration of the externally added catalyst HA. Now we can replace the value of concentration of intermediate 1 from the equation 2 in equation 1. So here is my equation 1. In this equation 1 we will replace this value with K concentration COH concentration HA. So rate of the polymerization, which is equal to rate of disappearance of monomer, will be equal to K3 capital K COOH HA in bracket close multiplied by the concentration of the second monomer, which is hydroxyl group. So the entire equation will be Rp is equal to capital K. Here you keep it in mind, this capital K is the equilibrium rate constant for my reaction 1. This is my first reaction of this entire mechanism, where capital K is equal to a small k1 over small k2, and k1 and k2, they are the forward and backward rate constant. Correct. So rate of polymerization Rp will be equal to capital K multiplied by K3. K3 is the forward rate constant in step 2. This is the K3 multiplied by the concentration of the carboxylic group multiplied with the concentration of the catalyst and multiplied with the concentration of the hydroxyl group, or in other terms we can say the concentration of the diacid, concentration of the diol, and the concentration of the catalyst. So this equation 3 is the reaction kinetics for the step polymerization reaction. Okay, so after developing this equation number 3, there are two possibilities now. First possibility is that the reaction is self-catalyzed. Self-catalyzed means instead of taking a catalyst HA, which is basically an acid and which is capable of donating one hydrogen, so this is a weak kind of acid. So instead of using catalyst, the carboxylic or diacid monomer itself can act as a catalyst, and this kind of the reaction where the diacid itself is acting as a catalyst will be known as self-catalyzed type of reaction. Another possibility is that we are adding externally catalyst HA to the system. So the rate kinetics will be different for these two conditions. So first of all, we will see the self-catalyzed reaction. So here diacid monomer can act as a self-catalyst, and equation 3 can be rewritten as K3 COOH square, because in this equation instead of considering HA we are considering one more time COOH, because carboxylic acid or the diacid itself is taking care of the catalyst, means it is acting as a catalyst. So this will be COH square multiplied by the concentration of the second monomer or the hydroxyl group. We can combine capital K small k3 in another new constant K, and this rate of polymerization will be equal to K COOH square multiplied by concentration of hydroxyl group. So my equation 4 is the governing equation for the self-catalyzed step polymerization rate kinetics. Okay. Now to obtain high molecular weight polymer, equimolar ratio of the diacid and diol is required. That's been the concentration of the diacid and concentration of the diol in step polymerization should be exactly equal. Then only it will produce a high molecular weight polymer. Otherwise, what will happen if there is some one monomer in excess? So what will happen? The carboxylic group will be attached to the both end of the chain, and in that case no further reaction will be possible with the monomer, because COOH is excess and it will end cap the growing polymer chain. So this is a prerequisite for high molecular weight polymer, that the reactants or the monomers are taken in equimolar ratio. So here symbolically we can say that the concentration of the carboxylic acid is equal to concentration of the hydroxyl group, and we can represent them as capital M, where M stands for monomer. Both of these are the monomers, so we will represent with the capital M. And instead of taking minus d by dt concentration COOH, we can write simply minus d by dt concentration M, where M is the concentration of the monomer, and equation 4 will be reduced to K M cube, because here COOH square multiplied by the concentration of OH. So this is also M, this is also M, so it will become concentration of M cube. Now we can integrate this equation with respect to concentration and time, and considering that the reaction is starting at time t is equal to 0 and the reaction is continued for the duration of t, such that the initial concentration of the monomer M dot is reduced to the concentration M. So M is the concentration at any time t, and M naught is the concentration of the monomer initially taken where t was 0, means at the initial stage of the reaction. So by integrating it, we will get minus, this minus sign comes from this equation itself, and again minus half multiplied by 1 over M concentration square, and the limit is from M naught to M. Similarly, K can be, KT will be integrated T from 0 to T. So this will be KT minus 0, so 0 is 0, so nothing is changed, it's KT. And here my equation, we can take out this 2 to the right hand side, and the final equation will be something like 1 over concentration M square minus 1 over initial concentration M naught square is equal to 2 KT. Now since the concentration at any time t is equal to the initial concentration of monomer M naught multiplied by the M naught dot P, where P is the conversion. Let's say after certain time T, conversion is 60%. So the value of P will be 0.6. That's mean the 60% of initial monomer taken has been converted into polymer. So M naught multiplied by 0.6 will be a factor that has already been converted into the polymer. So the concentration of the remaining monomer will be just 40% of initial concentration taken. So this is the relationship. M, concentration M at any time T is equal to initial concentration multiplied by 1 minus P, where P is the conversion. So we can replace the value of M with the value of M naught 1 minus P. Why we are trying to avoid M? Because the value of M, or the concentration of the monomer, is a transient factor. It is not a constant with respect to time. It is continuously changing. So it is very difficult to define something which is continuously changing or which is in transient in nature. So we are always interested in some constant values. We are always interested to develop an equation having constant values. So here in this equation, the initial concentration of the monomer taken M naught is a constant value, and 1 minus P, where P is the conversion at any time T. So from our pilot plant result, we are always aware about my conversion value with respect to time. So we will replace M, concentration of M, with M naught 1 minus P, and this equation will be, you can see the mathematical treatment of this equation, and final equation will be 1 over 1 minus P whole square is equal to 2 times KT M naught square plus 1. So this is my final equation for self-catalyzed polymerization reaction, and this equation is an equation of a straight line where y is equal to 1 over 1 minus P whole square, and with respect to T. So what will be my M? M will be 2k M naught square. Here I have written M is equal to 2k M naught square. So we are plotting a graph between 1 over 1 minus P whole square with respect to time on the x-axis. So we are getting the experimental data denoted as cross, and this is the straight line drawn which is a result of my mathematical model. So here we can see that there is some deviation from my mathematical equation that predicts a straight line with respect to experimental data. Experimental data is deviating in the lower conversion region, as well as experimental data is deviating from the mathematical model in higher conversion region also. Particularly we can say in case of kinetics of polyester, the experimental data will deviate with conversion value less than 80%, as well as it will deviate for higher value of conversion higher than 93%. In other words, we can say that this mathematical model that we have developed, this is applicable only for the region P is equal to 0.8 to P is equal to 0.93. Okay, rest of the part, my mathematical model is not suitable to predict the kinetics of step polymerization reaction for polyester resin. Okay, so this is the problem, but always nothing is perfect when we are developing some type of kinetics, even though this kind of equation is very useful, very helpful in the reactor design for the polymer. Okay, now what is the reason for this deviation? The reason for non-linearity? The reason for non-linearity are different for lower and upper conversion region. In lower conversion region, low slope indicate basically low rate of reaction. Low slope that represent lower value of rate constant is because of the polar nature of the diacid and diol present in the system. Okay, because my diacid and diol both are highly polar molecules, and because of the high polarity, the rate constant is inversely proportional to the polarity of the reactant. Okay, so in initial lower conversion region or the conversion region below 80%, the reason for deviation is because of the presence of the polarity of my reactants. And in higher conversion region, the reason for deviation is lower rate due to loss of reactant at high temperature. What will happen when we'll proceed at conversion more than 93%? Lot of exothermic heat will be generated, and because of the evaporation of the monomer, because some portion of the monomer will go off by evaporation and it will go along with the water that has to be continuously removed from the system. So loss of the reactant will actually responsible for the lower rate of reaction. So these are the two different regions for two different regions: lower region, lower conversion region, and higher conversion region. Okay, so this is the end of my 16th lecture, and thank you very much for your patient hearing. Thank you.